Hi students, in this lecture we are going to learn electric potential difference. Let us see how this is defined. The electric potential difference is defined as the work done by external agent in moving a unit positive charge from one point to other point slowly. Let us see what is this. Let us consider, just imagine there is no electric field in this entire space. I am repeating. Imagine there is electric field in the entire space. Okay. And what is the cause for electric field that is not required? It can be like due to a point charge, maybe due to many point charges or something else. So just we have to focus that there is electric field in this entire space. Okay. Right. Now in that electric field, we are taking one point charge. Let us say it is a Q naught. So we are taking a point charge Q naught in that electric field. Okay. Suppose if we release now this charge, if we release now this charge, it starts moving because electric force acts on that. Because electric force acts on that. Because of that force, it moves with acceleration. So now what I'm saying is, let us move this charge from one point to other point, from one point to other point slowly. Slowly in the sense its speed is almost zero. Its speed is almost zero. Okay. Then see what happens when we are moving this very slowly. From work energy theorem, work done by external force plus work done by electric force. This net work equal to delta K. And we are saying that moving this charge very slowly. Slowly in the sense speed is almost zero. That means delta K becomes now zero. Okay. Then work done by external force is equal to negative of work done by electric force, right? And this negative of work done by electric force is equal to delta U. So now we are defining potential difference. Potential difference as work done by external force in moving a unit positive charge. That means by Q naught. Okay. But by external force, work done equal to, by external force, work done is equal to delta U. That means change in potential is equal to change in potential energy per unit charge. I am repeating, change in potential is equal to work done by external force upon charge, or you can say per unit charge. If this is equal to 1, by external force work equal to delta V, right? If if Q not equal to 1, then delta V equal to delta U. So potential difference is equal to change in potential energy per unit charge. Otherwise, it is work done by external force in moving a unit positive charge slowly from one point to other point, right? So this is definition for potential difference. So from this what we can say is if a charge moves through a potential difference of delta V, then increase in potential energy is equal to, or we can say change, it is equal to Q into delta V. Okay, that means if a charge moves from low potential to high potential, then delta V will be positive, right? Because moving from low potential to high potential means delta V value positive. That means delta U value positive. That means whenever a charge moves from low potential to high potential, its potential energy increases. If charge moves from high potential to low potential energy decreases. Okay. So definition for change in potential difference is work done by external force per unit charge. Now let us apply this to find the potential due to a point charge. Let us consider there is a point charge, it is a Q. So we want to calculate at some distance r what is the potential because of this charge. What is the potential because of this charge at a distance r? At a distance r, what is, sorry, this is distance r. What is the potential? So here what we are doing is now we want to calculate what is the potential, sorry, what is the change in potential energy. Okay. For example, we are moving a charge Q naught. We are moving a charge Q naught from infinity up to this point. So from infinity means for this system, potential energy. Earlier we have discussed that potential energy for two particle system equal to K into Q naught by R, right? But here initially separation equal to infinity, bringing Q naught from infinite separation. That means initially potential energy is 0, or I can call it as U1, okay, or U initial. Finally, distance equal to R. That means finally potential energy how much? Q naught by R. This is now final potential energy. Now, potential at that point because of Q is equal to potential at that point, that is distance R, minus potential when distance infinity is equal to how much? Is equal to change in potential energy, that is K Q naught by R minus 0. Okay, this is now potential difference. What is this? This is a potential difference which is equal to K Q naught by R, right? So this is now, sorry, wait. This is now change in potential energy upon Q naught, right? That is equal to K Q by R. So this is the potential difference. Potential difference. So V of R minus V of infinity, separation infinity. Okay. Now, if you assume that, if you assume that, if we assume that potential is 0 when separation is infinity, then potential at that point where distances are becomes kq by r. Okay. So in case of point charge. In case of point charge at a distance r, what is the potential? That is a kq by r. Now, how we got this value means, if you take assumption that at infinite distance, potential because of this is zero, then we get now this condition. So whenever we are using this result, we have to keep in mind when distance is infinity, potential is zero due to point charge. Okay. Like this, we can calculate potential due to a point charge. Right. For example, let us take, let us consider we want to calculate potential potential due to a uniformly charged ring. So this is a ring which is uniformly charged. Its a charge is a q. It is equal to, take it as small r. Okay. Now we want to calculate because of this on its axis at a distance x. What is the potential? Okay. Now if you observe, each and every point charge on this ring is at the same distance from this point, and that distance is square root of x square plus r square under root. Right? I am repeating. Each and every point on this ring is at a distance of square root of x square plus r square from this point. So potential at this point because of this ring is equal to V equal to K, where K is 1 by 4 pi epsilon naught K Q by distance equal to square root of R square plus X square. Right? And if you observe carefully, potential due to positive charge is positive. Potential due to negative charge is negative. Or we can say same thing here also. Due to point charge at a distance r, potential is kq by r. Right? If charge positive, potential positive. If a charge negative, potential is negative. Right? Okay. So this is now definition part. Right? It is defined as work done by external agent in moving a unit positive charge from one point to the other point slowly. So it is delta U by Q naught. Okay. Right. Now focus on relation between electric field and potential. Relation between electric field and potential. See how to get it. Right. Earlier, if you remember, while discussing work energy power, there we have discussed relation between conservative force and potential energy. I am writing here. Relation between conservative force and potential energy. That is that is F bar equal to minus del bar into U, right? Minus del bar into U. Now here electric field also a conservative field. So electric force also conservative force. So in the place of F bar, what I'm writing is, in the place of F bar, it is a Q into E bar. So Q into E bar equal to minus del bar into In the place of potential energy, it is taken as charge into potential. Okay. Now Q gets cancelled. It is now E bar. E bar equal to minus del bar into V. That means electric field is equal to negative of potential gradient. I am repeating, electric field equal to negative of potential gradient. Okay. And if you see negative sign here, along the field direction, potential decreases. What is it? Along the field direction, potential decreases. For example, for example, electric field is along x-axis. Let us take different color. Let us take field is along x-axis. Okay, this is x-axis. Then let us consider points here A, B, and C, and take one point here on y-axis, that is D. According to this, see what we can say. Along the field direction, potential decreases. That means potential at A is greater than potential at B, and at B potential is greater than that at C, because along the field potential decreases. Along the field potential decreases. Now we can say one more point here. Along the field potential decreasing means opposite to field potential increases. And one more thing, if you take normal to field, see carefully. I'm taking here y-axis, okay? Normal to field. Field is along x-axis. If we are moving along y-axis, potential does not change. Get the point. That means here what we can write. VA is greater than VB. VB greater than this. But VB is equal to VD, because along y-axis there is no change in potential. The relation is field is only along x-axis. Therefore, normal to field there is no change in potential. Or if you imagine here one plane, okay, then what I can say is in that plane at each and every point potential is the same, and we can say that is equipotential surface. What is that? Equipotential surface, and that we discuss after this one. Now let me conclude here. Electric field is equal to negative of potential gradient, and negative sign indicates potential decreases along the field, right? Okay. Let us take one simple problem, that is, suppose we are given potential. Let us take here potential. It is changing only along x-axis. So V equal to x square. It is changing only along x-axis. Then what is electric field intensity? Given V equal to x square, potential changes only along x-axis. What is now intensity of electric field? Okay. Then see what we are doing. So E bar equal to minus del bar V. That means E bar equal to, it is equal to minus del bar. It is now I can write dou by dou x of V. V is now x square into I cap. Okay. That is equal to derivative of x square with respect to x. It is 2x. This is now minus 2x I cap. Okay. Like this, if we are given potential, we can find a field. So here what it says, Electric field is now along negative x-axis. Okay, along negative x-axis. Because x square, it indicates that potential is increasing when x value is increasing. Right? So E bar equal to minus 2x I cap. So direction of field is along negative x-axis. Right. Now, if you think the reverse way, we are given electric field and how to calculate potential. Okay. Right. So connect now those two. Focus now definition part for change in potential energy. Change in potential energy, that is du equal to negative of work done by internal conservative forces. It is now electric force, right? Work done by electric force. Integration of, okay, right. Now see here what we can write. This is taken as integration of q into dv, right? Because change in potential energy equal to charge into potential difference, and that is equal to minus work done by electric force, that is electric force is q into e bar, q into e bar dot, it is a dr bar. Okay, now q gets cancelled both sides. It is now, let us take, I am taking from a to b, a to b, then this will be va, and final value is vb. Okay, then see what we get. vb minus va is equal to minus integral e bar dot dr bar. Okay, so if you are given electric field vector and if they ask what is a potential or potential difference, then we have to take minus integral e bar dot dr bar. If we are given potential and if they ask find e bar, then we can take directly minus del bar into v. Here there is no dot, no cross. Okay, this is called negative of potential gradient. And we are knowing what is the meaning of del bar, right? I am writing once again here, del bar. Del bar is equal to I cap into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z. Okay, right. Now what I am saying is, here we are saying along the field potential decreases. That means normal to field. Normal to field potential does not change. Let us take, I'm taking a different color. Right. Let us consider there is a point charge. What is it? It is a point charge. Because of point charge, electric field will be radially outwards. Right? And say how to say that. If you imagine a unit positive charge here, this repulse along the line joining them. So if you take anywhere, it will be along the line joining them. Therefore, because of this, field will be radially outwards if charge is positive. Okay, and along the field potential decreases. Get the point. Now, if you imagine one sphere, if you imagine one sphere, imagine a sphere. Okay. Now, electric field direction is radially outwards. What is it? Direction of electric field is radially outwards. Means at each and every point field is normal to surface. At each and every point field is normal to surface. That means on the surface of the sphere. So if you imagine one sphere by taking that charge as center of that sphere, at each and every point field is radially outwards, or you can say normal to surface. That means on this surface at each and every point potential will be same. Therefore, because of point charge, equipotential surface will be spherical. Suppose if you take line charge, I think you can guess it. If you take line charge, suppose charge is positive. If you imagine one cylinder at each and every point, at each and every point, potential will be same. So because of line charge, equipotential surface will be cylindrical. Okay. And there is one more, that is, if electric field is uniform at each and every point, if electric field is uniform at each and every point, then what we can say is, you can imagine a plane which is normal to direction of field. That means in case of uniform field, equipotential surfaces are planes. They are plane. And you can see here nodes correspond to that. Right. So this is till now what we have discussed, right? So relation to electric field and potential. And we got equipotential surfaces because of point charge is spherical, because of line charge it is cylindrical, and because of if field is uniform, it will be plane. Okay, right.